Next, we have Truyen Tran presenting, sounds great to me actually, learning to remember more with less memorization.
Thank you. My talk today is it's about memorizations in neural networks. So you can see from the picture here is the recurrent networks is equipped with a external memory module. Then this work is done by myself and the two co-authors, Hung Lee and Professor Svetha Venkatesh. So we can think memory-augmented neural networks as either recurrent networks or standard feedforward networks with an external memory module. So it's designed to capture the long-term dependencies, which we wish to have in a lot of real-life experiments. And somehow it implicitly model the skip connections, which we know that have learnings. It provides a constant path length from the input to output, and in the process is help reducing the gradient vanishing problems. So here's an example of the well-known models, neural Turing machine. It was invented 5 years ago. So it have the controllers that read the input and produce the output, and in the process it reads to the memory and read from memory and write to it. The process is actually quite complex because a lot of operations are involved because we would like to have the entire network to be differentiable. So it involves a lot of attention in other operations, quite expensive. The problem with the networked memory-augmented network today is that we don't have very good theoretical understanding of how the memory works and in what's the case it works best or not really work best. There has been a number of previous works to improve the situations using intuition like location-based writing and readings with temporal linkage, or use other tricks we know from the computer's network, computer like least use writings and other sparse access to deal with the big memories. But however, our understanding is still very limited, and the networks are quite expensive to run and to train. So our contributions to these problems are, first we derive some measurements on how the network memorizes input over time. And secondly, we propose a few tricks to deal with that, so to get better memorization with less reading and writings into memories. So there are two tricks. One is uniform writings, another one is cache uniform writing. For the matrix, because we don't have very good definition or understanding of how and why the memories works and store information. So we start with a very simple notion of state transitions of the hidden state, HT, which depending on, like for example, we assume it's depending on the previous state and the input of the current state. So in effect, it stores all information from the history. So we define a notion of remembering called CIT, where I it's the input index, and T the current hidden state. So it measures, it somehow captures the notion that how much the state remember the previous input. Because we can intuitively you can see that if the derivative is 0, then we know that the h doesn't depend on the change in x. So we can assume that quite little information being stored in the state. So to measure the average memorization capabilities, we take the average of those CT over time and divide by t. So we call it it's I, it's index in lambda. So we figured out a couple of properties. One property that we proved that there exists a number lambda that captures the kind of decay effects of how the states remember the information in the past. And as in lambdas, because if lambda is smaller than 1, and we know that it's decaying over time, and basically forgetting the states it forgets what we read before, long before. So that was the case of standard recurrent neural networks. But for the memory-augmented neural networks, we have an external memory of D memory slots. And the case is a little bit more complex, but still the formula is quite similar. So the average memorization is still depending on a couple of things. One is the number of memory slots, which is like intuitive. So with more memory slot, we can remember more. Another one is depending on a parameter called Li, and it depending on depending on lambda, which is measuring how fast the forgetting happens. Because of these measurements, so we can think of a couple of ways to improve it. One is just to increase the number of slots in the memories, which is reasonable, but it could be expensive because most of operations are linear in terms of number of memories. And also increasing the D forever doesn't help either because it stops us from doing good compressions, right? Another trick is to make the decay rate lambda close to 1, which is not easy because we don't really know how to estimate lambda. So the question is that given a fixed number of D and lambda, can we optimize the index L by arranging the optimal writing occurrences over time? So we figured out another property, quite nice one. So given the D memory slot, so it's a sequence of length t's. So the sequence length t's and the average memorization can be maximized by a very, very simple rule that all the indexes L's are equal to T over D plus 1. It's very, very simple rules. So that suggests a couple of, at least one trick for us to do. One is that we can approximate both solutions by define writing rules of the big M here is a memory attempt T. So every fixed number of steps we write to the memory, otherwise we keep it a constant. Right? So it's very, very simple rules based on the previous theorem. However, it's based on two assumptions. One is that all time steps are equally important. Another one is that all information are equally important to remember. So those assumptions are okay if the task is like a copy. So we try to memorize everything, right? And the data is quite simple, doesn't change very much. However, in practice, sometimes it's quite unrealistic to assume that way. So for that, we propose another solution, which is called cage uniform writings. So there is a cage in the process, so that every few steps, maximum length L, we cage the information that the hidden stage produce over time. And then only at certain time step, we commit the memory, those caches into memories. And because we like to reduce information, so we use attention to pick the right time step to write into the memory. Right, so those are two solutions that we propose, and for the rest, I would show the few experiments that we prove by example that it works well. And for here, I think the examples on the neural Turing machine and the differential neural computers. with and without the uniform writing. So it showed that for the task here, which is repeating the input occurrence twice, the two tricks actually improve the accuracies and it reduces the reading times. For other tasks, for example, to memorize the input, the trick actually improves the accuracy in both the copying and reverse the task. In the reverse one, we have the sequence of integers, and the task is to try to output a reverse sequence of that. It's quite simple, but the LSTM would fail on this task because it doesn't know how to capture the very long range dependency. It's a sequence very, very long. The NTM and the NCs are better, but we can do even more with the uniform writing strategy. But if the task is to memorize selectively, we don't need to memorize everything, then the cage uniform writing strategy is better. So that agree with the theory that we proposed before. The other experiment is on the sine wave, and we have the first half of the wave, and then try to predict the second half, with and without noise. So in all cases, it proved that the writing strategy, the uniform or case uniform writing strategies, achieves better accuracies. The same result we achieved with the flattened MNIST data. With every pixel becomes a point in the neural networks, in the recurrent networks. Then finally, we have the result with the document classification, and every single word is iterated in the INN. So this one has been well studied, and we have a quite good result in the literatures. And what we saw here that we can achieve quite competitive results with the quite sparse writing into the memory. So that is the end of my talks, and if you'd like to hear more, I'll be presenting at the poster session today.
Thanks very much. Do we have a question while the presenter sets up? Okay. In that case, maybe I'll ask one. So these memory-based methods, they seem a little tricky to get going with respect to hyperparameter choice, that they can be very sensitive. The additional hyperparameters you introduced, how tricky is your method with respect to things like that? You've already mentioned that in uniform writing, the frequency can have a big effect depending on the task.
So that's true. It's quite tricky to train. Actually, we didn't do a lot of tweaking. We use standard implementations and use quite default settings. Our contribution is quite empirical based. So the hyperparameter was estimated from the data. It wasn't tuned by hand. So that was the main things.
Thank the speaker one more time.